So WikiModel's a website. I developed it a few years ago, and anybody can have immediate access to the application by going to the website, and there's no downloads. And we'll go through an example to kind of show sort of how it works and what you can do with it. So why did I create WikiModel? It's because it's a tool I wish I had when I was working in the life science industry for various problems of fitting models to patients with to model patients with type 1 diabetes. And when I did this, it took me a long time to code the model, and also every time you have to change the model, you have to do some coding. And with ODEs, it's especially more time consuming, because you have to create the function with the ODEs and then to fit the ODEs to fit the model to data, it requires additional coding, and you have to make sure the timing is all right, because the time in which the experimental data is collected is different maybe from the simulation and things like that. Obviously today, with all the large language models like ChatGPT and things like that, coding's become easier. And that's a good thing. But I find that it still only gets you maybe 75% of the way there. So again, it's a web-based software tool for simulating and fitting models, and I wrote it specifically for ODEs, to solve ODEs, where you have to sort of worry about integration and step sizes and all that good stuff. And this sort of handles all that seamlessly. And it'll handle any number of differential equations or closed form equations, and it'll simulate and plot results on the screen, and it'll handle discrete inputs at sparse times and fit your model to experimental data. And it actually also automatically figures out if linear or nonlinear least squares is required, and uses the appropriate fitting routine. And lastly, you can also, if you're a teacher and you want to share your model and data with your students, you can do that. You can share your models, you can keep it private to yourself. You could share it to your class, or you could share it to the public. So we can go into an example here, and here's an example where I go with my cousins. I used to go in the wintertime to go ice fishing with them in Minnesota, and we used to sit in this shack where we had holes in the ground, and we would fish. So on the bottom right is sort of a picture of us all sitting in this shack, and you could see there's a heater here that's kind of keeping us warm while we're fishing indoors and having a good time. So the problem we'll go over, or the question we'll ask is, can we measure the rate constant of the shack at which the heat is being lost? And also, can we measure the power of the heater when it's on? So that's sort of the example we'll go through, and let's use WikiModel to find out. So before we go to WikiModel, we have to figure out what the equations are. And really, there's only one equation, and you could start with your power equation, or rate of change of energy, and you can, with a little math and physics, you can convert the rate of change of energy to rate of change of temperature. And this is sort of the formula everybody knows and loves, that has to do with a rate constant when you have an indoor temperature and an outdoor temperature. Now, the only difference here is I added sort of an additional rate of change of temperature, and that's due to when the heater is on. And so I've converted sort of the power of the heater, dq dt to dt dt. If I know the density the specific heat of air, as well as the volume of the shack that we're in. So basically, we just have one simple equation. So now I'm going to bring up WikiModel to see how we can sort of simulate this. So let me bring up my page. So here, here's the equation. It's the same as what I had on my slide. Now, if you look at the equation, I have well, actually, let me simplify it first a little bit here. So I have my outdoor temperature is minus 11 degrees, and then I have a heater, but this heater was only on for a period of time, and we'll go over that a little bit more. And this is just the rate of change of temperature that you saw on my slide. I have some conversions to get from my parameters that are in units of hours to the -1 or degrees per hour to go into seconds, because my time that I'm plotting is in seconds. So, and what you also can do is you can input your data or upload it. And so here I have measured temperatures. I've measured every minute for quite some time. And you could see that you can plot them. And so my starting temperature, my initial temperature that I measured is 19.14. So I'm going to type that in as an initial condition. So this is my initial condition, which I got from my data here. Now, if I don't know what my rate constant is, but I'm going to guess. I have to give it sort of a guess. I'll say it's 0.2, and I don't know what this input rate in degrees per second is of the heater when it's on. So, but what I could do is I could hit simulate. Actually, let me make it smaller again. So just to make the graphs look, let me hit it one more time. So you could see that I've got two graphs here, right? So the bottom graph is sort of when the heater is on and when the heater is off. And with heaters, they generally turn on until they turn on when you've dropped below a certain temperature, and when you've reached another temperature, a high temperature, it turns off, and it sort of zigzags back and forth. And you could see the data that I plotted is in the temperature data that we're measuring is in the black points, and the simulated temperature is this blue line. And you could see that the simulation doesn't fit the data well, but what you can do sort of with this tool is you can also say, hey, I want to fit my temperature variable to the data that I typed in my data sheet. And when you're ready to do that, you hit fit. And boom, you could see that now you've got your simulation that fits your model fits the experimental data quite well. And so what you can then do is you could say, okay, my actual fit parameters are, I have this time constant, the rate constant of 0.3, and my units are in inverse hours, and my T dot on, which is the rate at which the heater is increasing trying to increase the temperature of the room, is at 37 degrees per hour approximately. So here, that's an example of how you can use a WikiModel to solve sort of like a scientific problem, right? You're trying to figure out what's the power of the heater and what's the rate constant of the room. And the other nice thing you could do is, like here, I gave my initial condition from my data, but and so what's happening when you look at the plot is it goes through the first data point, but it doesn't go through the other data points. And I have no reason to believe that my first data point is any more accurate than the others. So what I could say is, instead of giving the initial condition as a numerical value, I could give it as a variable. So I'm going to add a new parameter, and I'm going to call it temperature, temperature in, and I'm going to call it, I'm going to give it naught. So that's my initial condition. And I'm going to say, well, it's got to be close to what I measured. So I'm going to put in 19.14. And then I'm going to change this initial condition to that variable. So this becomes T in, and then O. Now if I hit simulate, and it'll simulate based on these initial parameters. And now if I hit fit, now it actually doesn't go through the first measured point, and that's more accurate because, you know, there's no reason to believe why the first measured value is precise, is accurate, and the rest are not. So what it did is it actually thinks that the initial condition was closer to 19 degrees instead of 19.14 degrees. But so here's an example again where you can use WikiModel to solve sort of a problem in your classroom. If you have a scientific problem that you're trying to, you know, not only simulate, but you have experimental data that you're trying to fit the model to. So I'll go back.
Sami,
Yeah.
So you can upload the data from what kind of, like a spreadsheet? Is that?
It's a text file. It has to be a tab delimited text file.
Okay.
Yeah. So or you could type them in manually. So, but yeah, you can, there's a tab here where you can upload your workspace from tab, and you can upload the equations or the data by using this button here. And you can also download the results, which I do a lot. So I download the results if I want to plot them in a different program or so on and so forth.
And how big a data set can this thing handle?
I don't know what the, you know, I think as big as really, I haven't really tested it. I don't know if there's a limit. Obviously, I wouldn't type in too many.
Yeah.
I would upload it if it was more than, you know,
Okay.
a few points.
You.
But I think it works pretty well. I haven't seen, you know, I haven't tested the limits, but I think it works pretty well for any reasonable, you know, anything even much bigger than this should be fine. The other thing is, you know, when you simulate it, you have to give it, I'll go back to my slides real quick. So so this is just sort of, we went through this already. I just put it in the presentation in case Brian, if you want the slide deck to share, that way they can walk through it while they're going through the simulation themselves and kind of see the step-by-step procedure. So here's, you know, the other thing you have to do is you have to specify, you have to plot something in order before you hit simulate, otherwise it won't be happy. So, you know, we plotted three things. We've plotted the temperature simulation, the temperature data, and the state of the heater. Let's see how I'm doing on time, 2:16. So let's see. So, you know, so the original question is, what's the rate constant? We could pull the rate constant directly from the fit parameters over here. That was 0.3. And we have to convert, you know, our output for the other parameter is the rate, is sort of the rate of the rate at which the heater is increasing the temperature of the room. And that was in degree, that was, you know, 35 degrees per hour. So we have to convert that to a wattage using the formula. If you know the density and the volume of air as well as the specific heat, you plug it in the formula and you end up with 182 watts. Now 182 watts I know is not, you know, the wattage for a heater is much higher than that, but that's the total wattage of the heater. This is just the wattage that's used to increase the temperature of the air in the room. It's you know, there's a lot of wattage going to heat other parts, you know, other objects in the room, and heat loss going to the outside. So, but so that's sort of the answer that it came up with. So that's an example. You can actually increase the complexity of the problem and say, hey, instead of just a one-room shack, what if I have a four-bedroom house where I've got vents in every room, and I'm still, and also, so instead of one compartment, I have now 4 compartments. And here, I won't go through it on the website, but you can click on this link and it'll take you there. And I actually developed this model for a smart home startup that was looking to use sensors, a network of sensors, to evaluate HVAC efficiency and problems in the house. So before my second interview, I sort of put this model together because I knew what they were trying to do, and I presented it to them. And after that, they hired me. But I sort of wanted to sort of show how this model is a little more complex than the last one. So here we're simulating the outdoor temperature now. Instead of it being a constant, it's a sine wave where the lowest temperature is around 2 a.m. and the highest temperature is around 2 p.m. And there's 4 rooms, and also the state of the heater is built into the model. And how these thermostats work is when the temperature sort of has this half a degree swing. If it's half a degree above the set point, it turns off, and when it drops to half a degree below the set point, it turns back on. And so it just turns on, off, on, off. And what you see is that obviously at nighttime, it's on more than in the daytime, because in the daytime, the temperature is higher outside, right? And here, I show the temperature profiles of 4 different rooms. And what's interesting and what makes sense is that it's obvious that the thermostat is in this room number 1 with this brew profile. And that's why it has the tightest control, that it's this tight band of a half a degree. And this temperature 4 was a room with a very large window that had a lot of heat loss. So the time constant of that room losing heat to the outside was much larger. The bigger the K value, the lower the insulation, or the worse the insulation is. And so you could see the different rooms have different temperatures. And I'm sure you're probably in your house like mine, some rooms are colder than others, and that's why, because different rooms lose heat at different rates. And the thermostat is in the room that's the tightest control is obviously the one that has the thermostat sensor in it. So that's sort of, I never gave sort of a heat transfer problem before. I've done other examples in the past. This, like I said, this is my third time presenting, but some of these I've presented at previous years Simi-ODE expos, like the predator prey, second order dash pod, and the projectile motion, I think, is that one I gave last year, which is kind of neat. It's actually based on experimental data with a marble and a camera, and that was pretty neat. That's probably up on YouTube if you want to check that one out. But there's various others, so that's my that's sort of my my presentation on WikiModel. I hope it's something that could be of useful to others. And it's not the best thing since sliced bread. I think it could be improved on. I think there could be, when the user makes mistakes and things, it can give feedback. Right now, if you make a mistake, it just doesn't reply. It just doesn't come back with an answer. And so if I had more time and resources, I would like to make it better, but I sort of need sort of a critical mass to say, hey, yeah, this is something I would love to use. And if I get, if people are really interested in it, I put more time and resources into it.